So my name is Cyrus, as you know. I work in AWS. I'm Principal Solutions Engineer. I studied math and computer science undergrad, then studied cognitive science and neural networks, was called back in the ancient times, in the University of Toronto. So in 2016, at AWS, we embarked on a mission to basically democratize AI, deep learning specifically. So we're just a small group of us in the early days. The whole idea was, which is the core strategy of AWS AI, of which I'm a member of, was to make sure that more and more engineers and scientists of different basically disciplines can actually get engaged in deep learning and develop things that they want to develop. We develop a range of products, we're a range of open source software. We got Apache MXNet, we made an Apache project and incubating at the moment. And these are the very latest developments we've done. There are two things that I'm going to go through very quickly and magically within the 30-minute time that we have. So my mission is that you would be expert in 15 minutes, so you go out and start using them, or you curse me and never again come to any of my talks. So the barrier to entry is actually quite high when you try to do deep learning. It used to be worse. I remember we used to do more math than programming, and then it's more programming than math. But despite having libraries, it's still quite complicated because you have to know so much in order to get something working. So what are the challenges? The challenges are you don't have enough data, or basically you don't have the scientific expertise in your organization. You have a steep learning curve with a whole new range of tools. Like, for instance, millions of Java developers have no access to Python. They have to learn the language. They have to learn all the libraries around it. They have to learn pandas. They have to learn this and that. So, and that's very complicated for a lot of people. And then experience of optimizing what you do is the other thing. I'll give you an example. I came across in Tokyo a company that had one of these, basically a deep learning team who just copied things from the tutorials and then start training their models, could never go beyond 2 GPUs, and it would take about 2 days to train their models. Optimization of that took less than 2 days, and then the training went down to under an hour on basically running 8 GPUs and utilizing about 100%. And that sort of optimization is an experience that you can't, there is no compression algorithm for it. You just have to go through that over and over and over again in order to know what the key things are. So how are we addressing those? So for instance, one of the most popular things that I can do is the model zoos that give you the model to make it easier, while at the same time activates transfer learning. So you see that this is from MXNet. When I say pre-train equal true from a model in model zoo, it actually loads the model parameters and the weights for you, and then you can just change the final layer of it and train it again on your own data. That means for the amount of data we had gathered, we have done pre-training of this model. We actually have models that are ready for inference, or you can actually train them further. So through transfer learning, you don't have to go through a whole lot of pain of training your models. Then we have developed a whole bunch of toolkits, and we're not stopping. So 2018, we released Gluon CV, which is a computer vision toolkit with its own model zoo and 50+ algorithm in it, and the utilities. Gluon NLP for natural language processing, and 300+ embedding and language models in there. And then we published a book, Deep Learning to basically dive to deep learning. That is an interactive notebook-based book that you can actually use. And also Gluon, which is a part of the talk that we are going through today, that includes basically architecture search and ENAS, basically to find the best architecture for you, so that it makes the architecture network a lot easier. Then how about the learning curve of new tools? So we used to have the ND array that belonged to MXNet. We have changed that now to deep NumPy. So your exact NumPy code just simply works and runs on multiple GPUs, parallelizes, and that sort of stuff. And then we created also in 2019, we released Gluon TS, which is a time series toolkit that is just basically fully adopts pandas. Whatever you do pandas, it just works in there too. You just use pandas directly under it. So to make sure that we are becoming more and more compatible with the NumPy ecosystem, something that didn't exist in early days. So how do we deal with the optimization? So AutoGluon gives us AutoML is a full-on basically AutoML toolkit. It's used for fast prototyping, automated hyperparameter optimization using multiple algorithms, including the Bayesian models, and reinforcement learning. And it basically uses the state-of-the-art deep learning techniques, as I said, like for instance, for NAS and ENAS. And it provides you with a massive set of configuration options, which is also applied as default if you're a newbie. But if you want to go and optimize it, there are just tens of parameters that you can actually use for more advanced users. And the distribution computation is completely abstracted away. You don't have to deal with it. It just happens behind the scene. You just say, oh, I want it to be distributed. I want to have 3 GPUs, and that's about all you need to do. Everything else is done behind the scene for you, so we have removed that complication of distributed programming that used to be very much, I know, fun, probably. So let's go to Deep NumPy. What's the motivation? With the model zoos being developed more and more in every framework, so we are back to the vast majority of the time being spent on pre-processing of data. So pre-processing of data has become, again, this like the majority activity that you do. So, but then you want to run these things on basically multiple GPUs, parallelize your processing. So you have to, so things like NumPy wouldn't be able to do that. So everybody started developing their own set of data structure for it. And what we developed was the ND array under Gluon, under MXNet, sorry. And then what happened here was it was not fully compatible. Through not being fully compatible, then you would end up with some behavior you didn't expect, and you didn't probably enjoy getting strange, weird errors for something that is supposed to be similar to what you have been used to use. So we basically very recently released, as a part of a Apache 2.0 license, MXNet, basically for initially we basically created MXNet ND. When you see here, there are three sets of code in here. If you look at it, the one up here is just a pure ND array coming from MXNet. So what we do here, we're just simply trying to do a dot matrix multiplication. So you get basically ND random normal, you get a standard distribution with a shape of 1,000 by 1,000, and then you just dots multiply it by itself, and then you get the time. As you see, the time is here is basically 0.001, etc., etc. Then you could actually do that on a single GPU. You could also do it on a multiple GPU. On a single GPU, you repeat the exact same code. You see it gets faster, so that's very nice, and the array runs on GPU. And then you can do the same thing on NumPy, that you see, even when you're using CPU, there's a huge difference. The question is, can we get the familiarity of this and get the performance that we get from these other two code blocks? So that's what we just released recently. And that is the same thing. This is the same old NumPy code. As you see, the NumPy code runs on top. So rather than we had ND random normal, so we have NumPy random normal, and then it's the gain. That's the standard Gaussian distribution. And then you have here, get the time, then your multiplication. Next line, what we do, we simply import NP and NPX, and we say NPX set NP. That is telling us, even the, when the type of NumPy you're using underneath is going to be now deep NumPy. That has distribution capabilities, that has a whole bunch of GPU capabilities, and then you can run the same thing. So here, I have the exact same code that I had previously, plus I have just added a context to it. So everything we used to have, now you can identify a context for it, otherwise the code remains the same. So I'm telling here, your context is basically your GPU, the context here is GPU, and then I run the same thing, I get the GPU result here, 0008, or here I have not identified the next line, and then you see the time is going back to being NumPy-like. So this is a standard NumPy, and what we have in here is deep NumPy on CPU, and what we have in here is Was it? No, that's an ND array, sorry, on CPU. And what we have in here basically is going to be the deep NumPy. Oh, sorry, I had gone one slide back. Sorry, forgive me. So now that's the correct one. We have the NumPy, then we have the NPX, we have the deep NumPy on CPU and deep NumPy on GPU. So the comparison here, as you see, the deep NumPy on CPU, still massively faster than the normal NumPy. You can make it faster using GPU, but your NumPy code is identical. It's actually, the NumPy code hasn't changed at all. So through just telling the framework you're using deep NumPy rather than NumPy. Sorry for skipping backward a page by accident. It looks very weird. Any questions so far about deep NumPy? Now you can use deep NumPy the way it is under basically Torch users can use it, MXNet users can use it. You just simply are going to use NumPy, normal NumPy, and just change it to deep NumPy if you would like to, and is almost fully compatible. There are a few things we're still working on. No surprises in here, and no conversion, nothing is required to do here. Questions? No, good. So the next thing we did was AutoGluon. So AutoGluon is an AutoML toolkit that we're actively developing. We released it. It is now, parts of it is GA, and is again, it's Apache 2.0. So what we have in here is got different segments in it. So what AutoGluon does for us is trying to do the features that we have is trying to do hyperparameter optimization or and architecture search through different mechanisms. So what AutoGluon does in here, the first thing that you can have a certain number of basically there are basic tasks. So we're adding more tasks here. We are saying that we are doing to do an image classification. So you can also do object detection. You can also do tabular prediction. And tabular prediction is when you have a table and you want to basically predict 1 or 2 or 3 columns, multiples of columns from basically tabular data. What we have in here is that from AutoGluon we're using image classification as task, and then we set a data set to it, and when we say task fit. When we say fit, what it does for us is going to basically train the model based on the default values that we have is going to have multiple basically training in order to figure out what's the best basically set of hyperparameters is going to be set. So it uses, basically what it does multiples of strategies. You can use a strategy of using Bayesian hyperparameter optimization. I just talked about it just quickly later on. It can use random search. It can use reinforcement learning based on the strategy of search that it's trying to do. And it's going to be basically doing it automatically based on the hyperparameters that is in the first line in here is completely based on default values. So that's all you need to do. After that few lines, after these 3 lines, you have a data, wherever your data set is, you give it a data set, you give it a task, and then you say fit. It goes and picks up multiples of architectures. It goes multiples of number of epochs. It goes and figures out what basically decides about a random default set of your mini batch size. Basically your optimizer, it gets all of that, and then it applies hyperparameter optimization to that to figure out the best result for you and train your model and give you the best result. And that's all it takes. That's these 3 lines of code, including the import. Or you can change your default configuration in the second bit. And as you see in here, we're just trying to say, you know what, just don't use the random number of networks that we're giving you. Use multiples of networks, but the list that we're giving you, that includes ResNet 50 v1 and ResNet 50 v2. We could have also given it ResNet 152. We could have given it whatever. There are more than 50 different algorithms that you can actually identify in here for for image classification. There are less than 50, but there's, I don't know, 20-something algorithm that you could actually give a list of. So you don't want to go too crazy, because then it's going to take a lot of time and money to do that. But you can actually identify a list in here. Why would you do that? Since you're using transfer learning in here, so you want to use the models that have basically the best similarity to what you want to do. That Japan example that I gave you that from 2 days to under an hour for training. One of the things that we did, instead of using ResNet 152, we just used ResNet 50 because they were doing a very simple classification in there. So they didn't really need to have this very huge network in there. There were other things as well in there. Oh, by the way, to tell you how much the optimization can be actually important, that again, that Japan case, the customer that was trying to do that, the projected saving on training per year was about $22 million. So these are non-trivial numbers. When you do proper optimization, it's worth spending time on it. So you can also give it basically the next line, another basically thing I would have done is basically learning a scheduler. So we're just telling you there are two different strategies. There's a polynomial and a COSI learning rate scheduler. Any question about what learning or scheduler is and what we're using for? Question? Question? No? Good.
We can have also a question session at the end.
Okay. So, and the number of epochs, we say 4, so it creates just basically up to 4 epochs is trying to choose. So what new search algorithm we have in here? One is a Bayesian optimization. So what is a Bayesian optimization? I can give you a simple explanation of that. So a Bayesian optimization is using an acquisition function. And the way it does, try to imagine you are going to, so I give you a basically probability distribution versus expectation. So that's quite important here. So probability distribution can be very expensive if you have a huge space or you don't know how many items you have. But let's try with the smallest space. I give you a box. Inside your box, you have 10 green balls and then you have 10 red balls, right? So then you want to see what is the probability of things that you're trying to take out of that box. You empty the box, you count them all, and you say there are 5 of this and there's 5 of this, you put it back, and then you say, I know that the probability of taking the red ball here is about 50%, right? And then you take one, and then after you take one, you know a red is out, the next one is 4 in 9 to be red, or 5 in 9 to be green, so on and so forth. But what if you have about 200 million balls in there, and there are multiples of colors, and then it's no longer cheap to go and just turn it upside down and start taking a look at it. It could be worse, because it also could be from basically, there's nothing in there, but there is a little bit of a, like gun, and just keeps inserting balls of a certain color based on a certain formula. But so you don't even know, even if you have all the time and the money in the world to make that upside down and count it, you just can't simply know, because not every ball is in there. It's just being added to it as you go through. So that comes the notion of expectation. So the notion of expectation is coming from sampling and expecting what your probability distribution possibly is. So the way it works, so I give you a ball, I give you a box, and within it, there are a bunch of balls. I tell you there's a bunch of balls in there. I cannot tell you what color, I cannot tell you what distribution, I cannot tell you anything. Just go figure out what it is. So this is called the black box, right? It's the black box system. The only thing that you have, you can take balls out of it and say, oh, I took a red. Oh, I took a green. Oh, there's a blue in it. So as you go through, and then you start making an understanding of the world inside that box. So that's the notion of expectation. The way it works, so I take a red one, sample, I have a red. I would say my next ball is definitely going to be red. Not definitely. I expect that it to have a high probability of, probability of 1 to be red. And I take, oh, it's a blue. So I have done 2 sampling. I have a red and I have a blue. Oh, I expect that my next one to be 50-50, either red or blue. And I go and come back on with a red. Now it changes again the probability. So every sample I do, I put in a data set in the back, and whatever I observed here, it forms my opinion about the world I'm trying to look at it. So I have no idea what's in it, but I have an expectation. After I do 1,000 sampling, I have a pretty good idea about what the probability of the next thing is going to be. So this is Gaussian process in a nutshell. So when you're trying to do a little bit of a sampling. From the sampling that you do, you're trying to figure out what the basically future is going to look like inside that box. So for that, you need everything is about an acquisition function. What is an acquisition function in this case was me going there, sampling physically, taking that thing out. Now let's try to have a much better example of that. So the example is you move to Tokyo tomorrow, and then you want to drive to your office. And as you want to drive to your office, you are going to figure out that what's the expectation of how long it takes to go to work. So first, you have absolutely no idea. You have never been to Tokyo. You don't know how the traffic works. Nothing at all. You live in the suburb, and your office in the center of the city. So you say, I think it takes 200 hours to get to work. Just random number you start from. And then you go, and here and there, you basically stop and basically measure your time. So you need an acquisition function that tells you at what points do you actually want to measure your time. So probably you don't want to do it all the time on the motorway. On the motorway, say I'll just do it when I start, and I do it again when I get out of motorway, and then I do it every 3 street blocks. So first in the outer rims of the city, then you have basically larger street blocks, and they're not as busy, and then you get, so you have to have a smart function to tell you how frequently you sample in order to get the best results. Because if you sample too much, it's also very expensive. So what you're trying to do in here, you want to have an acquisition function that tells you where to sample. And that acquisition function here is just telling us where to sample. The way to sample, it wants to give us either maximum yield when you have very little uncertainty, or you want to sample in places that yield might be small, but you have a huge amount of uncertainty. So it's called balancing between exploration and exploitation. So to give you another example of that, now you have gone to Tokyo, you have gone to your home, you have gone to the office, you're going back, and now you want to go and eat. You go in a restaurant that is near your house and go and you like the food. And then do it again tomorrow, do it again tomorrow, do it again tomorrow, do it again the day after and the day after and the day after until you get absolutely sick of it. So the reason is, you know that it's a greedy selection. So your acquisition function is doing a greedy acquisition here. So what it does is say, I know there is a huge yield in here. I have been in that restaurant before. There is very little uncertainty about it. But then, since you're getting sick of it, otherwise you end up eating in the same restaurant every day over and over and over again. So you say, why do I not go a little bit around and try another restaurant? It might be really bad, so I never again go near it, or it might be really excellent, so I might actually achieve something in here. So that's called exploitation. So you want to balance between exploration and exploitation. So the more uncertainty you have, the more you might end up finding things that are brilliant and you had no idea about them. And the more you have tried things, you want to balance between picking the good stuff that you have already have an experience with. So that's what the acquisition function is trying to do for us in here. So here we are getting the maximum uncertainty. Here we're getting low uncertainty but a good yield. So that's all about basically balancing between the two, between exploration and exploitation. So that's a Gaussian process. So what you do, you basically, it tells you sample here, sample here, sample here. So the acquisition function gives you the future samples. You do a few samples, and from those few samples, you build an expectation of where the direction of your hyperparameters or basically the choice of your architecture should go. So that's Gaussian, 5 minutes. So I extensively talked about what goes in here. So the other thing we've done is reinforcement learning. Reinforcement learning is used in here. It learns, and it wants to basically maximize the reward of the architecture or your hyperparameter that you're trying to use. So reinforcement learning is different than supervised learning, and unsupervised learning is a different form of learning. Reinforcement learning is based on feedback from the environments. You've got an agent, and your agent interacts with the environment and gets rewards for it. Let's see how it could potentially work. So if you are playing chess, then every move you get a reward of -1. So that means for just wasting time you get punished. You want to finish your basically game as quickly as possible. And then at the end, when you win, you get 1,000. So the whole idea is you want to again build that expectation. How do I move in relationship with my environment. I make one move, environment throws something back at me, and I can move based on a series of policies that in chess would be basically the move that are allowed. So what you want to do, how do I move in order to maximize my reward and get to the final goal? So this is a reward-based system. This is a system when you can actually, your agent can interact with the environment, and based on the feedback from the environment, it can decide what action to do. Once again, there is exploration exploitation here involved. Once again, there is basically building of an expectation involved, depending on how you're doing RL. I'm not getting to the details of reinforcement learning. What else do? We do NAS. So NAS is that we want to find an architecture that maximizes the reward with the corresponding network that minimizes the training loss. So you want to do an optimization of minimizing loss, but you solve that optimization problem through maximizing rewards. And one of the things we have done in here is using reinforcement learning to solve that problem. So there are two ways of doing that. One is NAS. So you have a popular basically architecture space, like starting from the MobileNet series. And then you basically construct an RL, reinforcement learning, that does search and figures out what the best solution is. Apart from, so NAS is very expensive because what it does a lot of sampling, and when it does a lot of sampling, then it has to build these convolutional neural networks, train this and that, so that's very, very expensive. We have also introduced something I haven't put in here, it's quite recent, called ENAS. So ENAS is trying to do a different approach to that by weight sharing, so that means creating a supernet, and that supernet is an oversized net, and it shares the weights, and then it doesn't sample at each iteration. It batches a bunch of stuff, it samples at the end of it, measures at the end of, so it's going to be a lot less expensive. What else we're trying to do? In the future releases, we're going to have text classification. So that's the transformer and BERT. If you know these architectures, these are both from basically Google translation team. So there is on tabular data, we're going to have more implementations. We're going to implement YOLO, SSD, and faster RCNN, hopefully soon. So we're going to basically have a newer version of NAS. We're going to include Gluon CV and Gluon NLP integration, so you gain access to every possible basic architecture that is implemented in there. And more applications, including pose estimation that is already being included in Gluon CV to be added here, so you can create basically AutoML pose estimation. These are references if you want to take a picture of them. They're supposed to be useful. So deep NumPy documentation, also Gluon documentation, including the that AutoGluon, probably that wouldn't work. I hope it does. I hope it's not internal. But now you can also just search AutoGluon, and now there is basically a part of MXNet.io and GitHub. You can find it. So you can find more about Gluon itself, about how to develop neural networks using Gluon Crash Course. The book I mentioned is Dive to Deep Learning. Also, if you teach places, we put the university courses that we teach, we included in the same thing. So Alex and Mu have put their Stanford course in there, and I had done something in Hong Kong University of Science Technology, so I have to add my material in there. So actually it's ready to go training material. The NLP CV and the TS toolkits for different use cases. So before I get literally kicked out of here, I better stop now. If you have any questions, feel free.
Yeah, we have time for one question. Question here.
Thanks very much for the talk. Could you say something quickly about how deep NumPy is implemented? Like what language you wrote it in, what platforms it's available on? Will it just be available on Amazon infrastructure?
It's on MXNet. It's an open source, and you can use it under MXNet. So you can also import it in different platforms. So I think there is a PyTorch example of that. I haven't used it with PyTorch personally. I think there is a PyTorch example that tells the PyTorch people. Also, Gluon works with PyTorch. So the deep NumPy, as you see, when you basically it installs with MXNet, and then you can simply import it and just use the coding. For Torch, I'm not quite sure how to use it, how straightforward it is, but you definitely can use it with MXNet and Gluon.
Okay, thank you so much, Cyrus, for a great talk. Are you going to be here somewhere around for next?
Sure, I've got a flight about 5 o'clock. Got to pick up my suitcase from the hotel. So a couple of hours probably I can stick around.
Yeah, cool. So if you wanted to get more info from Cyrus on probably different fields as well, you can talk to him, catch me on the coffee break or lunch break.
So I'll be outside.
All right. Great. Yes. Just a moment.